Welcome to the Rich Report, a podcast with news and information on high performance computing. Today, my guest is from Samplify. We have the CEO of the company, Alan Evans. So, Alan, I'm going to hand it off to you.
Well, today we're introducing our software development kit and our profiler tool for our APAX software, which accelerates high-performance computing applications running on supercomputing data centers and on the cloud. So what Samplify is, we're a startup company based in Silicon Valley. We're venture-backed, and we also have strategic partnerships in the area of high-performance computing and imaging. And what we offer is a technology that reduces memory, I/O, and storage bottlenecks in high-performance computing, SoCs, and FPGAs. We make our technology available both as a software development kit, i.e. a library that can be linked into an HPC application, and also we make it available as a hardware IP core for integration into systems on chip and FPGAs. And the two are 100% compatible, allowing someone who starts with software to later take advantage of hardware cores as they become available throughout the data center. And what Samplify does with our APAX technology is shatter the memory wall. What is the memory wall? The memory wall is the gap between the performance you can achieve with Moore's law in doubling the number of cores on a die with each successive process geometry versus the gap that's created from that performance in terms of memory bandwidth, I/O throughput, and storage throughput. What we see here on slide 3 is a plot of the number of cores for Intel CPUs in blue. And what you see is even though the number of cores has been increasing, the bandwidth, either on the front side bus or through QPI, has stayed flat with each successive iteration. That story gets worse when we talk about GPUs. In the lower right-hand corner, with Fermi, NVIDIA had 448 cores on the die and 384-bit wide memory. And going to Kepler, the number of cores has increased by a factor of 3 to 1,536, while the memory width has only increased to 512 bits. So a 3 times increase in the number of cores with only a 33% increase in memory bandwidth. That's the memory wall. And the solutions to that are reaching their limits. Packages are already pin limited, so you can't add more memory controllers. Every bit of memory is 2 pins. So 512-bit wide memory means you already have over 1,024 pins on that package dedicated to memory. Pin density just doesn't increase with Moore's law. And the other solution is adding more cache. Well, when we already have 20 megabytes of cache on Intel Sandy Bridge, it's already starting to dominate the die area. So that's not a solution either. What Samplify's APAX technology does is solve the memory wall problem in a different way by making the numerical operands used in these calculations smaller. And we'll describe what we mean by that. So the result of the memory wall is that CPUs spend less than 10% of their time actually doing calculations and spend 90% of their time waiting for data, whether that's data that's coming from memory, whether that's coming off the hard drive or coming from another node in the compute cluster via MPI across InfiniBand or an Ethernet backbone. By encoding those data transfers with our APAX technology at an encoding rate of 2 to 1, we reduce the amount of time the CPU spends waiting for data. As a result, you get your results 45% faster, then CPU utilization goes up 80%. When you turn our APAX technology up toward 4 to 1, now we get over a 200% improvement in CPU utilization, going from 10% utilization to 31%, and the time to results is decreased by over 2/3. And time to results is one part of the equation. Power consumption is the other. Data centers these days are fundamentally power limited. You can get a certain size power feed from your utility company, and at that point you can stuff as many servers and as much air conditioning into your data center as you can to fill in that power limit constraint. But when you look at how that power is consumed within a data center, actually only 40% of it is actually dissipated in the CPU, with memory and storage taking up the other 60%. And so by using Samplify's APAX technology, we actually reduce the number of transactions and the size of the transactions going out to memory and storage, resulting in a 50% savings in overall power consumption at encoding rates of up to 6 to 1. So now when you consider the trend toward, ARM-based CPUs targeting data center applications around, the version 8 architecture, 64-bit, those are really promoting, going to market based on low power. Well, when the CPU is only 40% of the equation, the full savings of those ARM-based architectures really won't be realized if DDR memory and storage continue to dominate that equation. So Samplify attacks that 60% of the equation with our APAX technology, allowing these ARM-based architectures to deliver their full promise in terms of low power in the data center. And so there are three main applications where Samplify's APAX technology can be used in software. The first is really what we're calling big science, which is high performance computing and supercomputing. And fundamentally what we have is the problem of data sets, which can be a petabyte in size, getting distributed over thousands or tens of thousands of compute nodes within a supercomputing data center. And what APAX does is accelerate the I/O and storage-bound big science applications, achieving an improvement of up to 240% in terms of time to results. Here are some example applications within big science that we've been working with early access customers. Multiphysics, we can achieve 8 to 1 encoding. Climate modeling, 5 to 1 encoding. Point cloud modeling, over 4 to 1 encoding. Earthquake simulations, 4 to 1 encoding. K-means clustering, very important for financial modeling, 2.8 to 1 encoding. So an average of 3 to 8 time reduction in the memory storage and I/O transactions, resulting in a corresponding speed up in the applications that are performance bound by those constraints. Big data applications are another big area. There's lots of interest in adding, unstructured data to these types of analytics, in addition to structured data that can be stored in SQL databases. Lots of technology being applied to compress the unstructured data, but it's all really targeting the text-based fields. With APAX, we give companies doing big data analytics a means to encode all of their numerical data as well, and the benefit now is increasing the amount of data that can be stored really near line for analytics processing by a factor of 2 to a factor of 8. And with all of this data out there sitting in storage, it's inherently a storage-bound problem. And by increasing the throughput off of these storage arrays, we improve the turnaround time from taking this business data and turning it into business intelligence by up to a factor of 4. And as we talked about earlier, our APAX technology can be made available both as a standard software library running on Linux or Windows on Intel processors, but also as embedded software or as hardware IP cores. And a big trend with these big data appliances is actually creating custom hardware to do these big data applications, with a lot of encoding and compression technology moved much closer to where the data is stored, rather than waiting till it gets to the CPU. And cloud computing applications have all the issues of big science, but now being deployed on an infrastructure that you don't own anymore, or don't have control over. And now you have the problem of taking your data set, maybe it's not petabytes, but maybe it's terabytes, and uploading that to the cloud. Well, we have a 10 megabit uplink here with our internet access, and it would take us 9 days to upload a terabyte file to Amazon EC2. But if we encode that data set by 4 to 1, we can reduce that upload time to 75%. That really becomes a big component of the total cost of ownership of cloud computing. In addition, our APAX technology allows that data to be decoded on the fly while the computations are being performed on each of those virtual servers sitting on the cloud. And so we reduce storage costs by 75% with that same 4 to 1 encoding. And also, compute applications on the cloud are really inherently I/O bound. Cloud computing data centers don't use 40 gigabit InfiniBand like all the supercomputing data centers use. You're looking at Ethernet backbones and a lot of latency in your data transfers. So our APAX technology, by reducing the size of those data transfers, also decreases the total latency, speeding up these I/O-bound cloud computing applications. And when you speed up your application, that means you're spending less time on the cloud. And your cloud costs, time is money. And so if you're spending less time on the cloud, you're saving up to 2/3 of your cloud computing costs. So let me turn this over to our CTO, Al Wegner, who will introduce our APAX Profiler tool.
Thanks, Alan. This slide demonstrates that the APAX Profiler tool gives HPC scientists new visibility into their data sets. One of the challenges that HPC has, besides the memory wall, is really understanding the nature of their data. A lot of the input data that goes into HPC simulations, for instance, some of our customers working in climate simulations, seismic processing, and multiphysics, that data comes from sensors. And the sensors typically have 16, maybe 20-bit A to D converters. But for convenience of computation, all of the input data typically is cast into 32-bit and 64-bit floats. Unfortunately, most of the HPC scientists that see the data after that believe that all of those 32 or 64 floating point bits are equally useful. So the purpose of the Profiler tool is really to give users new insights into their data, and then to demonstrate that if they want to encode their data by a factor of 3 or 4 or 6, that the data actually is quite similar after decoding to what it began with. The metric that Samplify is using is called the correlation coefficient, and it basically says how many of the decimal digits of the original data are preserved in the decoded data. The upper left-hand graph of this slide we're looking at here is called the rate correlation curve. So the encoding rate is on the x-axis, and the correlation ratio is on the y-axis. And for this example, you'll see that there's a whole lot of 1s on that y-axis, and that the lowest number in terms of correlation we have is at around 5-to-1 compression, and that's 4 nines of correlation, so 0.9999 of correlation. And that typically means that you have 4 or 5 decimal digits out of the theoretical 6.5, 7 decimal digits you have for 32-bit floats. So for most customers, that is a surprising number, that there would be such a high correlation where you're compressing the data by a factor of 4. The other couple curves on the lower half of the profiler output window, the left-hand graph is showing you the input signal spectrum, so taking the FFT of that data and then displaying it, and then showing you what is the difference between the decoded signal and the original signal. So that is called the residual signal, and that's shown in the lower left-hand graph in red. So the spectrum of the residual signal is, in this case, about 8 dB below the lowest spectral component of the input signal. So this is something else that makes Samplify's encoding, APAX encoding, unique, is that the residual level is quite small relative to the size of the input data and the spectrum of the input data. So in summary, the profiler is a new tool that allows people to get a recommendation of how much encoding is possible for their signal. So that rate correlation curve is unique for their signal. And then it also lets them move the red dot, the operating point on the rate correlation curve, to a more conservative or a more aggressive level, and then shows them what the effect is both spectrally and in the time domain for that result.
So our APAX software is available as a software development kit. So it's not a standalone application by itself to be deployed on a supercomputing data center or on the cloud, but rather a software component that gets integrated into an HPC user's own application, or an independent software vendor might integrate with their application, just as they would other technologies like MPI or parallel file systems. We support both Linux and Windows, both 32 and 64-bit variants. It is extremely high throughput. So the key question is, can it keep up with the I/O and the storage throughput? And we do provide 200 megabytes per second of encoding and decoding throughput running in software on a single core on an Intel CPU. It's thread safe, so you can have multiple streams going simultaneously. The library can be called from multiple different processes running on the server. And again, this very unique feature is that the API for our software development kit is the same as it is for the software drivers that go with our hardware IP cores. So as HPC users APAX enable their applications, they will get to take advantage of future APAX enabled hardware as that gets deployed in the data center without having to recompile their software. As you can see, the API is quite simple. We do an initialization, which creates a state structure. That's what allows us to do the multi-threading. There's a config encoder or config decoder call. This is basically passing in the parameters that came out of that profiler tool Al just talked about. And then from that point on, there's just calls to the encode and decode functions, passing pointers to the buffers for the raw data and the encoded data. And then when you're done, just release all the memory, and that's it. So very, very simple API, very easy to integrate into a HPC application or a big data application. All the user has to do is basically wrap their MPI calls or their major file I/O transactions with APAX encoding and decoding functions. So in summary, what we're solving is the memory wall on multi-core processors, and the benefit of that is basically lowering upload, storage, and compute costs while decreasing time to results, improving time to results for big science, big data, and cloud computing applications. All of our technology is now fully available as both the software development kit. The profiler tool is online. Go to profiler.samplify.com to try it out for yourself. And our hardware IP cores are also available and have been announced at the ARM Technology Conference a few weeks ago. So thanks for your time, Rich. Do you have any questions?
Well, yes. Thanks, guys, for that. So first question that comes to mind, I guess I want to just step back a bit. Are we talking about a lossy compression here? And then looking at the profiler, Al, I mean, how does someone judge what's the right level of 4-to-1 or type compression that's right for their app where it's got acceptable returns?
So I think the first thing to keep in mind is that the original data has an inherent accuracy and uncertainty associated with it. And so what the profiler tool is providing the HPC user that insight as to what is that inherent accuracy and uncertainty. And then consequently, how much encoding can we provide while still maintaining that initial accuracy or uncertainty around the original data.
So let me put a quantitative spin on it. Let's say you had a sensor that was measuring, I don't know, the brightness of a laser or the power of a laser, and you have a transducer that is monitoring that, and it's going to a 16-bit analog to digital converter, A to D converter. That 16-bit converter generates samples that are in the range of plus minus 32,000. So you're going to have about 4.5 decimal digits of accuracy. For convenience, HPC users are just going to cast that integer into a 32-bit float, and anybody that sees that waveform afterwards is going to say, well, I guess that has 7.5 decimal digits of accuracy because it's a 32-bit float. What they fail to realize is that came from a 16-bit A to D converter that only had 4.5 decimal digits of accuracy. And furthermore, depending on whether the sensor was measuring a noisy signal or whether the 16-bit A to D converter actually only had 14.5 effective bits, there are sources of uncertainty that make that statement quite questionable, that you actually have 7.5 digits just because you happen to cast your original integer into a 32-bit float. So all that is really complicated. There's actually a small branch of scientists and researchers in HPC that are researching this, and their field of discovery is called uncertainty quantification. So we think that the APAX profiler is going to make them very happy. So for the first time, you actually have a tool that says, how good are these numbers? The short answer to your question is, it is effectively lossless. And that's the important part about APAX encoding. If you have 5 nines of correlation, in other words, 5 out of 7 decimal digits are the same, the magic of Samplify APAX encoding is that we know how many of those decimal digits out of 7 actually have useful data in them. And while scientists may quibble about that result, we'll be announcing in the future some partnerships and some beta users in seismic, in climate modeling, and in multiphysics that have indeed verified that wherever we recommend the operating point goes, they have run the APAX encoder at that rate and have seen 0 difference in their final results.
Well, that's very exciting. So can you guys describe how would this work in an accelerated computing heterogeneous environment? You mentioned Kepler, right, where you've got to get the data across the PCI bus into the Kepler accelerator, crunch on it. How does this work? Does it compress the data before it goes to Kepler, and then you're doing operands on compressed data, or how does it look?
Well, to solve the PCI bottleneck, which is a big one for GPU computing for things like CUDA, you do need to have a device that encodes and another device that decodes. So what we have planned is that the x86 machine would encode the operands being sent over to the GPU via a slightly modified version of CUDA mem copy. That's the host to device and device to host software mechanism that's used to transfer data from the CPU's memory to the GPU's GDDR5 RAM. So on the GPU side, you would decode that data as it's being loaded into the multiprocessors that are on the GPU side. So this could be done in software on both sides. Alternately, Alan mentioned that we're also announcing a hardware implementation, an IP block, if you will, that chip companies can integrate into their processor. The great advantage of having APAX in RTL is that it's a tiny little block. It would fit under a bond pad, which means a very tiny amount of area of a chip, but it would give you a huge bang for the buck. If you think about GPU computing having 4x more GDDR5 memory, or 4 times the bandwidth to that GDDR5 memory, that would be a huge win. No one is talking about anything like that in terms of bandwidth and capacity uplift for HPC. That advantage also goes to disk drives, where you have parallel file systems like Panasys, Lustre, and GPFS. If you want 4x more bandwidth and storage today, you got to buy 4 times more hardware. What the APAX technology offers you is in software encoding, decoding today at around 50 megafloats per second. You can have that 4x uplift. When companies like Intel and NVIDIA and AMD hopefully someday integrate APAX technology into their chips, you'll be able to get that uplift at probably 10 times that rate at 1/10 the power, because the computations will be done in a tiny little IP block rather than the CPU and GPU itself.
And, guys, I first heard of this kind of computing approach back when Oracle rolled out the Exadata. It's an engineered stack where they compress the data and then do their database work on it and logic. Can you contrast how the APAX compares to that compression that they're using, and what's similar, what's different?
Yeah, that's an excellent question, Rich, and I'm glad you brought that up. The technology you're describing that's used for database companies like Oracle and SAS and SAP is called columnar compression. Columnar compression's been around for about 5 to 8 years, and it's still, for a lot of people, considered a whiz-bang technology. As you know, databases are organized into records, and all those records have fields in them, and the definition of what's in each field is held in the database's schema. So what database researchers realized a few years ago is, let's say you have a database record that includes a customer name, an address, a phone number, and a zip code. They realized that the zip codes actually only have 5 characters in them, and very often, depending on how you organize your database, the zip codes are very redundant. So what they decided is that it's a lot easier to compress a bunch of zip codes as a column than it is to compress database records as a row. So unfortunately, the columnar compression does little more than deduplication. It basically says, here's some records that we have that are the same. Let's replace those with an index into a lookup table. So certainly that process is lossless, which it should be for database applications. And therefore, the compression it gets depends on how likely the records are. Very often, Exadata and applications like that for databases will brag about 50-to-1 compression. Well, all that means is that they organized the database records so that they have all the zip codes in one region. The records are all together. So you get 50-to-1 compression because everybody has the same zip code. So I don't really call that compression in the sense that we're doing it, where we actually look at the data and detect how accurate it is, or uncertain, and then make the adjustment to the encoding rate based on that uncertainty.
I think you got to keep in mind when you're looking at database analytics, which is really what big data refers to, is the analytics side of that equation, not the transaction processing side. On the analytics side, you're really taking, what could be hundreds of terabytes of transaction data and distilling that into what we call business intelligence. So, I want to know, what's the average selling price of Nike polo shirts amongst men from 18 to 24. etc. Right? It's that averaging that's a key part of the analytics equation, and that's what makes our APAX technology actually ideally suited to these types of big data analytics problems, because it can be used both on the structured data side, which you would traditionally put in an SQL database, and it can also handle the unstructured data side, where you're really dealing with numbers.
So guys, I guess kind of a wrap up here. We're coming up on SC12. What are you guys doing to enable people to kick the tires on this and see if it's going to work for them?
So we'll be demonstrating our APAX profiler at SC12, and we'll also be demonstrating our hardware IP demo, which shows the benefit of accelerating a point cloud application when running the APAX IP block in hardware.
And our booth number is 4151 at Supercomputing this year.
All right, sounds good. Well, gentlemen, I want to thank you once again for coming on the show today.
Right.
Welcome. Our pleasure.
All right. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.